So the next topic we'll cover, and maybe a couple of sessions, will be on planning. So planning is finding a sequence of actions to reach the goal, okay, from the present initial state to reach the goal. So that's to find a sequence of actions. Um, so what you do is you search through a space of actions, okay, and find it in a particular sequence so that particular task is can be carried out. Now we can see that there's a lot of the common between the planning and search techniques. So search techniques also, you are starting from the start state and going to the goal state. Okay, but there are some differences between planning and search. Okay, so in planning, what you find is the world that you're considering is much more complex. For example, you can even think of space missions, etc., where you're going to come up with a plan, and it's actually very complex. And if you are going to use the same techniques which you are using in the search techniques, you will find that the branching factor is going to be extremely high. So for example, if you have a start state where you are at a particular position, okay, and you are going in the forward direction, and you say that you need to go from the house to the some shop. If you are going in the forward direction, the branching factor will be really high, right? You have to say there are so many places you can go to in the real world, right? So the branching factor will be too high, and it will not be able to use this type of technique. So planning in that way is a little different from the search technique that we are going to use. Okay. So what happens is that in the case of planning, we need to characterize what is not changed by a particular action. For example, if you say that block X is put on block Y, right? Now the rest of, the rest of the blocks world, or the rest of the world that you are talking about, remains the same. Okay, and it may be very complex. You cannot express everything in every step, right? So what you say is it does not change the other things in the world, and this is what is known as the frame problem. Okay, so the frame problem is something which you need to think of in the case of planning problems. So whatever you are working on, only that will change. Okay, nothing else will change. Okay, so you are trying to find a series of actions to achieve a particular goal, and you express your problem by using what is called the planning domain definition language, or the PDDL. Okay, that is the language you are going to use, and in that language what you are going to basically do is you are going to specify what is your initial state, what is your goal state, and what are the actions that you can actually carry out. Okay, so when you come to what is called the action schema, okay, you say action S, which means at a state S you are carrying out action, a particular action, okay, and maybe the action is A, and you use things like result AS. In other words, in state S, if you carry out action A, then the result that you get will be got by result AS. So when you look at the actions, every action is given by the action, the precondition, and the effect of that action. So what are the preconditions that need to be satisfied to carry out this particular action? And once you carry out the action, what is the effect of carrying out that action? So these are the things which you have to give whenever you talk about an action. Okay. For example, if you say fly the plane P from some particular location to some particular location, what are the preconditions you need to have? At P from. Okay, so the plane has to be at from and plane P. So plane P has to exist there, and you have an airport from and an airport to. And what will be the effect of this? The will not be at P from and at P to. The plane will not be at the position from, but it will be at the position to. And you can have the same thing with specific values. Okay. So fly a particular plane 1 from San Francisco to JFK. Okay. So this is the precondition. So the plane is at SFO and plane P1, and these are the two airports that you have, right? So the preconditions give the states in which the action can occur. The action can only occur if the preconditions are true. And the effect defines the result of executing the action. So if you carry out this action, what is the effect of that? And if you have a set of action schemas, okay, so this defines an action schema for a particular action. If you give the action, the precondition and the effect, that's called an action schema. So if you consider a planning problem, it consists of a number of action schemas that are given along with the initial state and the final goal state that you have. So the whole thing together defines your problem. The initial and goal state are a conjunction of predicates, right? And the representation of actions consists of the action description, the preconditions and the effects. For example, here this is the PDDL, which is the Planning Domain Definition Language description of an air cargo transportation planning problem. So you are giving the initial state here at C1 SFO, so that's the carrier cargo unloading, at C2 JFK, at plane 1 is at SFO, plane 2 is at JFK, cargo C1, cargo C2, so C1 and C2 is the cargo, plane P1, plane P2, at airport JFK and airport, so this is your initial state, and your goal state is that C1 should be at JFK and C2 should be at SFO. So you need to put the cargo and take it and unload it in the other place, right? And these are the actions that we have. Okay, so you have load, you have unload, and you have the action fly. So using these three, you need to find a plan so that this goal occurs, right? And your solution could be something like this: load C1 into plane 1 at SFO, fly P1 from SFO to JFK and unload C1 from P1 at JFK. And similarly, load C2, P2, JFK, fly P2 from JFK to SFO and unload it. Okay, so this would be your total solution to the problem, or this is the plan that you are getting for this particular air cargo transportation planning problem. Here is another example, the spare tire problem, right? So initially your tire is flat, you have a tire spare at flat axle. So the flat tire is at the axle and the spare is in the trunk, and your goal is at spare axle. You want the spare to be at the axle, right? And you have all these actions possible. So remove object from the particular location. So you have a precondition and an effect. Action put on T on the axle, and lastly leave overnight. So these may be three actions which are available, all of them with preconditions and effect, right? and this could be a solution: remove flat from the axle, remove spare from the trunk, put on spare and the axle. So this would be your full plan to put the spare onto your axle. Okay. And here is the blocks world problem. So when we talk about the blocks world, you have blocks which are there on a table, right? So they can be either on the table or they can be on another block, or you can have another block on that block, right? So these are all the possibilities that you have, and you can have a start state, right? And you have a goal state. So how do you go from the start state to the goal state? And suppose this is your start state and this is your goal state. Your initial state will be on A table, on B table, on C A. Okay, so C is on A and B are on the table, and block A, block B, block C, they are all blocks, and clear B and clear C. So when you say something is clear, it means it doesn't have any block on top of it. And the goal is on B, on AB and on BC, right? And these are the actions that you have. You have move B from X to Y, and you have action move to table, right? So those are the two actions that you can use. So this could be your solution. So if this is, you can move to table C, okay, and then move B, move to table, move B from table to C, okay, on top of C, and you can move A from table to top of B, right? So you get this. So this is what is called the blocks world problem. So when we look at the blocks world, you can have a number of blocks which are on the table, and you have a robot arm. Okay, so the robot arm is either empty, it's not gripping anything, okay, or it could be gripping a block, right? So when you say gripping without any value there, it means that the robot arm is empty, or it could be gripping some block, okay. And you can have on XY, or you can have clear X on table X. Okay, so these are all the predicates which describe the blocks world basically. Okay. So if you have a table like this with the blocks in this way, you can describe your initial state like this: on table A, on BA and clear B, on table C, on DE, clear C, okay, on table D, gripping is empty, okay, so the robot arm is empty, clear E, okay, so this whole thing together gives you your initial state. So what are the rules that you may have to describe what you mean by clear, etc.? Okay, when you say clear X, it means there does not exist any block Y such that on YX. And when you say not on YX, it means on table Y. And when you say gripping is empty, it means it's not gripping any Y for all Y, right? So this is your initial state, and these are the actions that you can have, right? So each action we can say that this is the action, right? And this part gives you the result of the action, and this gives you the precondition of the action. So if it is A implies B implies C, A is the action, B is the result, and C is the precondition. So when you pick up X, okay, what happens? As a result of picking up X, the robot arm is gripping X. And what is the precondition? It should not be gripping anything, the robot arm, and X should be clear and on table X. Okay, so every command will have the action, the result of the action, and the precondition. Put down X, when you say put down x, the gripping will become empty and x will be on the table and x will be clear. And the precondition should be that it is gripping x, only then it can put it down. And stack x on y. If you want to stack x on y, what will be the result of that? On xy, and gripping will be 0 and clear x, right? And the precondition should be clear y and gripping x. So in this way, every command, you have the action, the result of the action and the precondition. So this is one way of representing the actions. So what do you mean by the frame problem? So like we said, if you are talking about y, z, if you are unstacking y and z, right, then it does not have any effect on x. So if as a result of doing this, if on table x, then precondition also on table x. Stack xy on table x on table x. So that's what we mean by the frame problem basically. So something remains the same. Okay, if some part of your blocks world is changing, the rest of your blocks world remains the same. And this could be your state, right? On table A, on B A, clear B, on table C, clear C, on table D, clear D, and gripping E. The robot arm is gripping E. So that is one way. Another way is that every action that you take is described as a triple, like given over here. Okay, you have P, A and D, right? So what does this? So there are 4 operators: pick up, put down, stack and unstack, and it's expressed as triples of description. The first element is set of preconditions. So if you have a particular action, for example, if you take pick up, what are the set of preconditions? Okay. Second is the add list. In other words, if you carry out this action, then you need to add these predicates into your knowledge base, right? And the third is the delete list, or you have to delete these descriptions from your knowledge base. So for example, pick up x, what is the precondition? Gripping must be nil and x should be clear now on table x. And what is the add list? You have to add to your knowledge base the fact that the robot arm is gripping x, and you should delete from the knowledge base that x is on table and gripping is nil. Okay. So similarly, all the actions that you have will have the preconditions, the add list and the delete list, which can be used to update your knowledge base as you carry out these various actions. Okay, now if we come to situation calculus, what we mean by situation calculus is that you are talking about a particular state in time. Okay. So you have a sequence of situations. You have situation say S0, then situation S1, situation S2. What we mean by that is that you move from situation S0 to situation S1, then from situation S1 to situation S2. So you have a sequence of situations. Okay, so which will be something like taking care of time in a way, but you are not taking time explicitly, but you are taking it as situations. Okay, so let's see how you can carry out the logic when you are using situations, right? Every predicate has an extra situation argument which will tell you the situation at which it occurs. Okay. So you can say at agent 1 1 S naught, which means that the agent is at position 1 1, okay, the coordinate of the point at situation S naught, and at agent 1 2 at S1, and at situation S1 the same agent is at point 1 2. Okay, so that is one way of representing the the fact that the agent is moving, right? Another is that the result, so you use what is called the result of moving forward from situation S0 gives situation S1, right? So you use a result to show how the world changes basically. Actions are described by stating their effects. Okay, for example, if you take for all x and s, present x s. So at situation s, x is present, okay, and x is portable, right? Which implies that as a result of grab x, okay, so if x, if you grab if you grab x at situation s, it means that you will be holding x. That's the effect, right? And not holding s as a result of release s. So if you are carrying out the action release at such situation s, it means that you will not be holding x. And frame axioms, like I said, when you are talking about a particular part of your state, another part of the state doesn't change, holding x at a situation s, and if the action is not released, then holding x as a result of as. So that means you continue holding, okay. If the action that you use is not to release, then you continue holding x. And not holding x at situation s, if you are not holding and you don't grab, okay, the action is not grab and not present excess, okay, and it's not, or it's not present at that point, then you continue not holding, right? So unless you're grabbing it or it is present there, etc., you continue not holding x as a result of a particular action. Then you have what is called the successor state axioms, okay. Holding x as a result as is equivalent to saying the action is to grab x and present x as and portable x, or that you are holding, you are already holding x at s and you are not going to release it. Action is not release, right? So you can see that a number of different situations can be very easily expressed, by using the situation calculus, and you can show how actions change the situation from say one situation to another situation, etc. So there are two types of search that can be done, forward search and backward search, just like we saw when we did state space search earlier, right? So it's similar to that. So forward search is, like I said, prone to exploring irrelevant actions, okay. For example, if you buy a specific book, you may have action buy ISBN with the effect own ISBN, okay. And if there are 10 billion books, there are 10 billion actions you can take, right. So it makes the branching factor very high. And the backward, which is also called the relevant space search, okay, because you are only going to search in relevant regions of the space. You start at a goal and apply the actions backwards till we find a sequence of steps to reach the initial state, okay. This is called the relevant space search, as we only consider actions which are relevant to the goal that we are using. So you are going to move in the forward direction, or you can move in the backward direction. So if you are moving in the backward direction, it's much easier to do and much faster, because you are only going to search only to in the search space those regions which are relevant to the goal that we are talking about, and it will not search the other regions of the search space. So here you can see in this figure, okay, the forward search, the A shows the forward search, okay. If at P1A and at P2A, right. So from here if you go forward, fly P1 from P1A to B, you move from point A to point B, and P2 will move from point A to point B, and so you can say at P1B, at P2B, etc., and you can go in the forward direction. But suppose your final thing that you want is at P1B and at P2B, you want both of them to be at point B, whereas now at the starting state they are at pointing, they are at point A. You can go backwards from there, okay, and come to the original position. So that is the backward search as compared to the forward search that we have shown over here. Okay, so one one planner. Okay, so we will talk about a few different planners. So the first planner that we talk about is what is called the partial order planner or the POP. Okay. So in the partial order planner, what you are going to do is you start with a minimal plan which only contains the initial state and the goal state. Okay. And at each step you extend it by achieving a precondition of a particular step. Okay. One of the preconditions of a step you achieve it by performing a particular action. So what you need to see is find the action, okay, whose effect is the precondition of one of the steps, and putting that action into the into your plan. Okay. Mostly like it is like a regression planner, because what you will end up doing is you have the start state and you have the goal state, and the goal state will have a certain number of preconditions which need to be satisfied for the goal to become true. So you take each of these preconditions at different points in your program, and you find the action such that the effect of that action will be that precondition of the goal. So here if we see, this is your spare tire problem, right? So what you do, like we said, is you have the start state and the finish state over here, and you go from the start state to the finish state. So you have an empty plan here with only these two. Okay, so you're starting from there, and if you look at the finish state, what you want is at spare axle basically. Okay. So if you want to have at spare axle, okay, and these are the start state, what are the things which are true at start state? What you have it at flat axle, at spare trunk. So this is what is true. So looking at the actions that you have, if you want at spare axle, what you have to do, put on spare axle. Okay, that will give you the effect which will satisfy this, right? So you put this and put the preconditions of put on spare over here, right? So once you do that, you have whatever preconditions which are left at the finish. Here there is only one precondition, but sometimes you may have more, and you have these preconditions. So how do you satisfy these leftover preconditions? At spare ground. So how do you do at spare ground? So you can do at spare ground by removing spare from the trunk. The effect of that is to have the spare on the ground. So that will have a precondition which needs to be satisfied, and you need to find the action to satisfy that. But in this case it's already satisfied at the start state, right? Then you look at not at flat axle. How do you take care of that? You need to remove flat from the axle, right? So what will be the precondition of that? You have to put it here, and that is already satisfied, right? So you keep doing this till all the preconditions are satisfied, right, of the entire plan. So you can do it in any order, right? You can do, if you had say 2, 3 or 4 preconditions here, you can do one precondition, or you can do another precondition one step, and you can do this. Okay, that's why it is known as a partially ordered planner. So you do this, and finally you come up with a complete plan to for this problem. So this is known as the partially ordered planner. So we'll stop at this point and continue in the next session.